All right, guys, I want to pick up where we left off yesterday. We were talking about conditional statements, correct? Yeah. So conditional statements, what I want to kind of show you or demonstrate with you is graphically, if I have this equation, 2x minus 1 equals 5, what I'm going to do is going to write the left-hand side as y equals 2x minus 1, and the right-hand side, I'm going to write y equals 5, okay? And those are only going to have the same y value, essentially, on the condition that the x values are identical. Does that make sense? Okay? That's what we're really doing there when we solve an equation. Okay? When the x values are identical, the y values end up being the same, or the only way that the y values can be the same is when the x's are identical. Does that kind of make sense? Okay. Now, as we work through an equation, as you analytically approach an equation, you start moving things over the equal sign using inverse operations and stuff like that, you transform the equation, and it is no longer what you started with. Does it make sense? So if I would have taken the equation 2x minus 1 equals y and y equals 5, okay, I guess let me rephrase it. If I would have taken the equation 2x minus 1 equals 5, and I would have started trying to solve that by hand, the first thing I probably would have done is added 1 to both sides, right? So when I do that, it gives me a side that is 2x and a side that is 6. Okay? And here's the idea then. That graph, and even the equation 2x equals 6 is different than 2x minus 1 equals 5, right? But because I did the same thing to both sides, okay, and I got a new representation over here, this is, if you look at the value, they look similar. But if I look at this graph in detail, that line right there is not the same as that one there, right? This horizontal line through 6 is not the horizontal line in the yellow that goes through 5. So I have a different representation in the background. But because I did the same thing to both sides, their values for x when their y values are identical is still 3. Does that make sense? Okay. So what we do, even though this is a new equation, all of the solutions to the stuff in yellow exist as solutions in the blue. And in linear equations, that's not something that should be all that mind-boggling to us. Okay? But let me demonstrate here where this is going to go in the upcoming sections. If I have, let's say, square root of x minus, let's go plus 2. Okay? If I've got that, and let's go y equals 2x. Let's go 1 half x plus 1. Let's see what that looks like. Okay. I don't like that. Plus 1 half. All right, so we would have an equation here that would be root x plus 2 equals 0.5x plus 0.5. Does that make sense? Okay. Well, if I was going to solve that, what we'd have to do is we'd have to square both sides, actually. Okay. So what I'm going to do over here on the right-hand side in the blue is I'm going to square this. So if I square that, what do I get? X plus 2. Okay. And now if I square this, now that's going to be a binomial square, so we're going to FOIL and all that kind of stuff. So what I'm just going to do is I'm just going to say 0.5x plus 0.5 and square it that way. And I get that image. Okay? Does that make sense? So here's the thing. Here's the question. How many times in the yellow do those two images, those two graphs cross? One time. How many times does it happen on the right? Twice. Okay? Now, if we go off of what I said when we were doing the lines, working with that linear equation, all of the solutions that exist for this, all of these solutions exist over here somewhere. Does that make sense? Okay? But not the other way around. Okay? Because one of the solutions in the blue is not a solution of the original equation, right? And this all happens because we squared things. That's the algebra that generated this issue. But let's look at the intersections here. If I look at the intersection of that and that, it showed it to me, but it put it on the wrong graph, so let's do it this way. That and that, so we get 0.383, right? Okay. If I look at the the intersections over here, we got point D, which is 3.83 again, right? So point B and point D, they have the same x value, 3.83. So that's showing me that 3.83 was a solution to the original equation, and it was a solution that showed up when we adjusted it by squaring both sides. But that negative 1.8 number, which is over there at point C in the blue, that was nowhere in the yellow, right? Does anybody remember what that point C, that negative 1.8 number would be called? Because it's not a solution for the original equation. Not imaginary. Extraneous. Okay? Extraneous just means to us it's an extra thing, it's an extra solution that does not work for the original equation. Okay? When I hear the word extraneous, I think of it being the combination of two words. Extra and erroneous. What's erroneous mean? Say something about me. That's mean. I'm stinky. That's erroneous. That's false. It's not true. Right? Does that make sense? It's an error. Okay? It's an errored statement. So when I put extra and erroneous together and I get extraneous, okay, in my mind, it means it's extra, but it's wrong. It does not become a solution for the original. Does that make sense? Okay? You think I'm stinky? Why can't you smell? You have diarrhea of the mouth. All right, so those are what conditional statements are. Conditional statements for linear equations, you're going to have one solution. Okay? Your y values are identical on the condition, or the left side and the right side are identical on the condition that you use that specific x value, right? Okay, you get one solution. This one here, okay? Go through the algebra real quick. What would you guys do first if you're going to solve this thing for x? I heard distribute the 2, okay? That's perfectly fine. So I distribute the 2. And I'm going to get 2x minus 6 equals 2x minus 6. Say again? So x is allowed to be anything in this case. Why did you say that? Right. So if I plug in 10 on the left-hand side, that's exactly the same thing as plugging in 10 on the right side. I'm going to do the exact same math, right? Okay. So what I look at here is that the equation, or the equal sign, is like a mirror. Okay? And if the left-hand side looks identical to the right-hand side, that's like me looking in the mirror, right? I got my face and I got my reflection. They should be identical, right? Okay? So we get what we call an identity here. Okay? An identity basically means you have, yes, infinite solutions. X can be anything. And if you don't recognize right away that you have an identity, because some people don't, they just kind of, okay, I got to add 6 to both sides. And I get 2x equals 2x. Okay, so then I got to subtract 2x from both sides and get 0 equals 0. And when I get down to something, wherever I'm able to recognize that I've got a true statement, and a lot of people feel most confident about saying they have a true statement when it's a number equal to a number, and those numbers are the same, right? So 0 equals 0. Or if I would have subtracted 2x from both sides right away, I would have got negative 6 equals negative 6, right? That's a true statement. When you get a true statement, it means you have an identity. No matter what your x value is, you're going to get a true result back. So an identity, I would write this down, an equation that is always true regardless of the variable input. And it does, you probably also want to add to that with linear equations, when you have an identity, you have an infinite number of solutions. If we were to graph those, if you remember back to Algebra 1, if I graph 2x minus 6 equals y, and then I write in the second line, I go y equals 2 times the quantity x minus 3, and I graph them, what's the image going to look like? It's going to look like the same line. You're going to have two lines that are on top of each other. So, let's see here. All right, so here I've typed them both in.
This time sophomores, last name P through Z. Sophomores P through Z. Please report to the high school gym for pictures. Thank you.
All right, so we then have those two lines intersecting, overlapping each other, okay, all the time. And no matter what point I put on there, okay, that point A, that x value is on both, right? So 7.17 is a solution because no matter what I put, 7.17 there, 7.17 there, multiply, combine like terms, that kind of stuff, you're going to get the same 8.34 back. We okay with that idea? Okay. Identities are huge things for us, especially when we get to trigonometry. If I graph, have you guys ever seen this before? That's a sine wave. Okay. When you guys are talking in your physics, who's taking physics in here? I'll ask you because I forget, obviously, but I'll ask you all the time. Who takes physics? Because this will be something, usually when I ask that, something follows that will be applicable to physics. When you guys talk about light waves, sound waves, electromagnetic waves, like when our Bluetooth connections are being made, okay, with Wi-Fi, radio waves, okay, they all travel this way. Okay, now sound waves are, a lot of times they're called longitudinal waves, but sound waves are compressional waves. So they take when I'm speaking, the particles in the air are compressing like that, okay, and they're reverberating back and forth, and that's what allows you to, that plays off your eardrum or whatever, and that's what allows you to hear it. But that can be modeled, that compression back and forth can be modeled using sine and cosine waves. Okay, so that's something we'll talk about in physics, but we talk about the mathematics behind it in the trig class. If I look at the cosine wave, okay, and all this stuff I talked about your radio. This is all how why you have like FM radio and AM radio, and why you have to turn it to a knob to a number. Okay, AM stands for amplitude modulation, so that basically says that you're going to change your radio to where your receiver to be able to read the particular amplitude of one of these waves, okay? FM stands for frequency modulation, which means it's going to be able to read how fast that thing is moving, how fast it's going up and down like that.
Spaced out. Spaced out in the gym. Thank you.
All right, so here's my question. If I do this, I'm going to write pi over 2 minus x. The green graph disappeared, right? But it's really on top of that red one. Does that make sense to everybody? So what we have here is an identity. If I would take the sine of pi over 2 minus x equals cosine x, that is an identity. No matter what I choose for x, I'm going to get the same thing back. Here's the purpose of identities for much of math after today, if I were in an equation and I saw sine pi over 2 minus x, that right there, that scares me. That green stuff scares me. It's just messy looking, right? But if I know what it is equal to, I can rewrite. I can replace that with cosine x, right? It's much like seeing 2 times the quantity x minus 3. That might look messy. I can replace it with 2x minus 6, what it's equal to, right? So when we start talking about identities, it's their purpose for us a lot of times in mathematics is to replace, make those substitutions to make our lives a little bit easier in the solving process. Say it again. No, so tangent is going to have vertical asymptotes. Looks like that. Okay. So tangent is, like if I go sine of x, there's sine of x, right? Let's divide it by cosine of x. What did it give you? Tangent of x. Okay. So that's all your SOHCAHTOA, and that's the relationship. That tangent is just your sine and your cosine divided by one another. And that's all stuff, that's a little prelude to what we'll do in trigonometry, all those little connections that happen there. If I'm looking at this example, okay, this equation, okay, what would be something that you guys would do right away? Okay, you're going to distribute. Okay, that's fine. I would do something different. And this is kind of what I want you guys, I want you to, you know that distributing is fine and it works. Let's get out of our comfort zone this year a little bit with our operations, because this is how I, like when I was in high school, I always did what I was comfortable with, right? It makes sense. I mean, that's human nature. But when I got to college, I realized, what I was comfortable with wasn't maybe all that efficient. Can I foreshadow and think about maybe an easier way to solve that and makes my life a little bit easier? Multiply everything by 2, right? Okay, multiply left-hand side by 2, right-hand side by 2. Now, when I do that, think about what I've got over here on the left-hand side. And I didn't space things out enough here to give myself enough room to, let me wipe that away. All right, so if I'm going to multiply over here by 2, okay, and then I'm going to come over here and multiply by 2 over here, right? Okay. Now, the idea here is when I multiply the left-hand side, I should have put parentheses around here, so I'll put those brackets. I don't know why that one bracket keeps disappearing. But I've got 2 times this new quantity of 1/2 times the quantity x minus 1, right? So ultimately on the left-hand side, how many things am I multiplying together? Multiplying 3 things together, ain't I? Because of the associative property of multiplication, I can rewrite this as 2 times 1/2 times the quantity x minus 1, right? When you see things in parentheses, again, we'll talk about this again here in a little bit, that, even though it's 2 terms, I'm just going to view it as it's 1, right? Does that make sense? That's what the parentheses say. We cluster that together and it's one object, okay? So I'm multiplying 3 values over here. Think about this. If x was a number, wouldn't this just be, like if x was 0, wouldn't this just be -1? So this is just a number times a number times a number. So I got 3 things. Now the associative property with multiplication allows me to just take any 2 of those that I want and multiply them together, right? And this is what Jimin was saying, where it makes most sense to multiply by 2, because those 2 things right there multiplied together give me what? Don't know why. I think it's because I wrote in white behind there. But those 2 things give me 1, right? And then I have 1 times x minus 1. Well, what's 1 times x minus 1? Just x minus 1. Okay? Now, on the right-hand side, it's a little bit different. On the right-hand side, I don't have 3 things being multiplied together here, right? I have 2 things being multiplied together. One of them is a quantity. The other one is an individual value, too. What do you have to do there? Distribute. So when I distribute, I'm going to get x plus 4, right? Okay, now there's no wrong answer to what we do next, but what is an option? Add 1 to both sides. So I get x equals x plus 5. What next? Subtract x from both sides, right? So if I subtract x from both sides, I would get 0 equals 5. Now, when I ask you like a step to do next, there's an infinite number of ways to solve every single equation, okay? But if we go off of our end goal of trying to essentially isolate the variable on one side and isolate constants on the other side, there's always going to be a most efficient way, right? Okay. Going through that, we get down to 0 equals 5. Is that a true statement? No. Okay. That's a false statement. Okay. And that's what a contradiction is. Okay. A contradiction right now, when I started the equation, it said that they were equal, right? But our math tells us no, that's a what we have just shown is a contradiction to their equality. They are not equal. Okay? Does that make sense, everybody? Now you could have right away subtracted x from both sides when we had x minus 1 equals x plus 4, and we would have found negative 1 equals 4. It's not the same 0 equals 5, right? So your information that might lead you to a contradiction might be different than the neighbor's information that led you to a contradiction, but they're both contradictions, right? Does that make sense? Okay. Why? Graphically, what do we have here? If I were to graph those two things, y equals this and y equals that, why do I know instantaneously? Okay, the two lines don't meet. That means they're parallel, right? Why are they parallel? Well, if I rewrote this left-hand side, would you guys agree that that's the left-hand side if I distribute? Would you agree that this is the right-hand side? What do you notice about their slopes? They're the same, right? Okay. Now, when the slopes are the same and the y-intercept is different, they're parallel, okay? So when the slopes are the same, that really only says, well, they could either be the same line or they're two lines that are parallel, right? You then have to look at the y-intercept to make sure that they are moved away from each other, okay? So that's a contradiction. How many solutions? 0, none, right? They do not cross, so there is no position where their y values are identical because of their x values being the same. Okay? So those are the three types of equations that we're going to come across.
Right direction at this time, freshman. Last names A through D, as in David. A through D. And report to the gym for pictures. Thank you.
All right, so I'm going to, just because of the time constraints, I mean, I don't think, because we all graduated 8th grade, that we can solve that example 1, right? Okay. Let's scroll down to example 3. 1051. So we got that example there. Okay, so this is a linear equation. Our variables are all x to the first, and they're all numerators. So linear equation, but there's fractions in it, right? And we're not fans of fractions, correct? Now you can, and in the past I've taught it this way, where we just leave them as fractions, just do our work, okay? But that makes you, if I'm going to subtract two fractions, I have a common denominator. When I'm left with a coefficient in front of my x and it's isolated, I want to multiply by its reciprocal, I can do it to both sides. And that's fine, that works. But what does the exact same thing as multiplying everything up there by a what? A least common denominator, okay? And here's the thing. People always ask me, or they tell me, a lot of you have told me this when I had you in previous classes. I got that same answer, but I did it a different way. Well, if you're a person that moves that 3/4 x over with x to the 6, or x over 6, and you move the 2/3 to the right-hand side, and then you multiply by the reciprocal of that x coefficient, whatever that ends up being, to both sides, even though your process was different, collectively that process generated an LCD that you multiplied both sides by. Does that make sense? Or all things by. So even though your structure might be different, the underlying procedures, underlying rules and theorems were identical. You just did them in a different order. Does that make sense? Okay. So how do I find an LCD? A least common denominator. Any ideas? I can't hear you at all. Okay. So he's saying find multiples of these numbers that all of these numbers will grow to, right? So, I mean, like a multiple of 4 is 8, right? But 6 and 3 can never get to 8 by multiplying by an integer, right? Okay. So what I always tell people is that you are trying to, through multiplication, find the smallest number that you can get these three things to grow to. Okay. So it'd be 12. Okay. Say again. Okay. So Jim is saying, can I just take 6 times 3, which is 18, right? Times 4, which would be 72. Okay. 72 is a common denominator, which will work, but it's not the LCD. And here's the issue. When there's variable components in the bottom, that gets really ugly and nasty. But if you forget at any time that you have to use the LCD, especially when it's just numerical, you can use any common denominator. LCD is just going to make it easier. Because if I multiply that first one by 72, then I'm going to have 18x left over. Does that make sense? Multiply the next one by 72, and I'm going to have, 24 left over. Multiply the last one by 72, and what's that going to be? That's the 18. I guess the first one would have been 72 divided by 12. Okay. Does that kind of make sense, everybody? Now, the quick way, eventually, obviously right now, because it's 6, 3, and 4, we know 12, right? Eventually, when it gets messier, the way of finding the LCD is that you're going to prime factor each denominator. Is that okay with everybody? And when you do prime factorization, you're going to break it down usually like 2 times 2 times 2 times 3 times 3 times 5 times 5, like 2, 3, 5, 7. Those end up being a lot of your numbers that we deal with that get broken down. We don't deal with very huge numbers that, like, you're going to have like a factor of like 11 and 13 and stuff like that. You could, but usually it's 2s, 3s, and 5s and 7s, that kind of thing. Okay. I always write things when I have like 4 was 2 squared, right? It's 2 times 2. If it was 2 times 2 times 2, which is 8, I would have written 2 to the third, right? And now the reason I do that is because I need to decide what components become part of my LCD. You start going through and say, okay, first thing is a 2, right? 2 to the first is this first one. Do I have any other 2s? That's always the question I ask. Do I have any other 2s as factors? I got 2 to the first, and I got 2 squared, right? So anybody remember which one I take? You take the higher one, okay? And the reason for that, when I take the higher one, it automatically at the same time takes that lower one. Does that make sense? Okay? So if I were just to take the 2 and leave that as my LCD, that doesn't incorporate the 4 into my LCD. Okay? But if I take the 4, it automatically incorporates the 2. So we always take the highest exponent. Okay? Now if I go to the next term, the next factor in these denominators, it's a 3. 3 to the first. Are there any other 3s that have a higher degree? No. So I just take 3 to the first, right? Okay? And then I look at this last one that I haven't dealt with yet, and it's 3 to the first again. I've already got that, so I don't take it twice. Does that make sense? So what's 2 squared times 3? That's your 12. Okay? Now, notation-wise, you're going to see people like do this. So I got to multiply everything by 12. That's what this is saying. You're going to see people write it this way. And that's fine. But the nasty part of that is that there's going to be cancellations happening a lot, and you get things confused. And the number one error people make there is that they multiply the x over 6 by 12, they multiply the 2 over 3 times 12, and then they write equals 3/4 x. They forget to distribute to both sides, right? So what I always do, and it eliminates that error, and it also eliminates errors made by canceling, is I'll just put a 12 with that first one, a 12 with the second one, and a 12 with the third one. Okay? Now, you guys probably learned that, that 12 and that 6 cancel, right? And what's it leave you with? 12 over 6 is 2, right? And I have then 2 times x. Okay? But the reason they cancel, think about this. I'm multiplying everything by 12. I'm taking x over 6, and I'm multiplying it by 12 over 1, right? Do it down here. 12 over 1 times x over 6. If I multiply straight across, I get 12x, right? Multiply straight across the bottom, I get 6, right? That can be rewritten as 12 over 6 times x over 1. If I multiply it that way, if I rewrite it that way, is that still 12x over 6? Yes, but what's 12 over 6 now give me? What am I able to do with that? I'm able to simplify that. I'm actually able to do that division. It gives me 2, right? Which is the exact same 2 that we shortcutted right here and said, oh, that actually gives me 2. Multiply 2 times x gives me 2x, right? Does that make sense? So part of this class, guys, I don't want to give you, like, because this is, I understand that some of you have, like, structure or procedural things that you go through, but you're not 100% sure why we do it, okay? My hope is that kind of demonstrates why we can just cancel that 12 and that 6, okay? There's a lot of things in this class that come from Algebra 1 or come from Algebra 2 that you guys have learned procedurally that you just do it, okay? But maybe you're not comfortable or understanding of why you do it. That's the why of that canceling. Does that kind of make sense? Okay? And those are the things that I'm really interested in, because you pick those things up, algebra's a cake. Okay? It's cakewalk. It's easy. Okay? Here, if I go 12 and 3, those are going to cancel, leave me 4, right? What's 4 times 2? 8. Okay? Now, the idea there is I was actually taking 12 over 1 times 2 over 3. Well, 12 over 1 times 2 over 3 gives me 24 over 3. What's 24 over 3 reduced to? That 8, right? Okay? And we'll do the same thing then in that last one. Those are going to cancel, leaves me 3. So 3 times x now gives me 9x. Okay? At that stage, I'm just going to leave that there. You guys can finish that. Okay? We get down to like 1-step, 2-step equations that are like linear or whatever, very easy. I usually don't go and solve for the x, and I'll just let you guys do that on your own. All right? Yes? So the next thing, let's look at example 5. Anybody remember what that type of equation is called? It's still linear, because all our variables are the first power and they're all numerators, right? So it's linear. But if it's a ratio equal to a ratio, back to geometry. Starts with a P. How would you solve that equation right there? What would be, if you didn't know, what was maybe the first thing you would try? Cross multiply. So what do you cross multiply with? Proportions, okay? This is a proportion. And we learned in geometry that the cross product of the extremes and the means should be the same, right? Okay? So you should be able to take the yellow objects, multiply them, and the blue objects, and multiply them, right? Now just remember, when you do that, you have to distribute. So when I take the yellows, it's going to be 16x plus 12. And when I take the greens, or the blues, I guess, it'd be 6x minus 12. And we can solve that, right? Okay. Here's my question. Is that still an equation that has fractions in it? Just like the last one we did, right? What could I have multiplied both sides by instead of cross-multiplying like that? Could have multiplied both sides by 12, right? That's the LCD. So if I multiply the left-hand side by 12, multiply the right-hand side by 12, what is going to happen between that number there and that number there? What's that going to reduce to? 3, right? So the 12 and the 4 cancel, leaves me 3. And now I would take 3 times that numerator, right? Well, isn't that exactly how I got 6x minus 12 previously? I took that extreme of 3, and multiplied it by 2x minus 4. Does that make sense? If I multiply the right-hand side by 12, the 12 and the 3 are going to cancel, and it leaves me with 4. I take that 4 times that 4x plus 3, and I get 16x plus 12, right? get the same exact thing. So what's that tell me? Cross multiplication automatically generates the LCD, right? So when I multiply in a proportion by the LCD or I cross multiply, it's the same thing.
At this time, freshman last names E and then Earl through H. Please report to the gym for pictures. And freshman letters E through H.
Does that kind of make sense? Like those guys, and I don't think we're doing anything here that's mind bending, right? Like this stuff is not anything that you've not seen before. But I want you to start thinking about the procedures, how they're conducted, why they're conducted, and that's going to allow you to pick up on the more complex algebra stuff that we do later on. Okay, I've told you guys this before. I think in geometry, you guys know what area is, right? You guys know what slopes are, right? That's calculus. That is all that calculus is. Okay? But you hear all these nightmare stories about people in calculus and it being very difficult, right? Okay? The reason calculus is very difficult is because of the algebra that's used in working with those areas and working with those slopes. But if we can become experts at the algebra, calculus is a cinch. It's easy. Okay? And that's what this class is designed for, is to prepare us for that calculus. Does that make sense? Okay, and I think it's not. I don't think you get good at algebra by just doing problem after problem after problem after problem and just doing the same process and procedure. Okay, you get good at algebra by understanding the underlying concepts of what allow those things to happen and why you can do those. Understanding your properties like the associative property, commutative property, distributive property, that kind of stuff. When to use them, when not to use them, when they apply, when they don't apply. Does that make sense, everybody? Okay, we'll stop there. Last class we got down to example 7, but we'll just pick up with that tomorrow, or I guess Monday. No assignments yet. Okay. Have a wonderful weekend.